Why were experts concerned about the 19th of December? That question began to circulate among observation teams when a series of real data caught the attention of researchers who monitor the activity of objects traveling through space at extremely high speeds. The date did not become important because of rumors or exaggerated ideas, but because it coincided with a measurable change in the photometric records that several telescopes captured almost at the same time. In a matter of minutes, the brightness graphs showed a clear variation, enough for the analysis centers to repeatedly review the values in order to rule out instrumental errors. Upon verifying that the measurements were consistent, interest grew because any sudden alteration in an interstellar object can reveal details about its structure and its behavior under the influence of solar radiation. What surprised the experts the most was the precision with which that change occurred. The 19th of December appeared as a marked point in the data, not because someone had pointed it out beforehand, but because the instruments recorded it directly. Comparisons with previous days showed that the pattern did not follow the expected line, and that led to a more detailed examination of images, spectra, and activity curves. Every observatory that had records from that period reviewed its own data to verify whether the behavior was repeated, and the coincidence between independent measurements reinforced the need to understand exactly what was happening. The scientific concern did not arise from mystery, but from the informative value of the observed variation. Interstellar objects are rare, and every opportunity to study them provides crucial knowledge about materials that did not form in our cosmic neighborhood. That is why that specific change raised so many questions, and this is where the explanations based solely on verified facts begin. Before we continue revealing why December 19th set off all the alarms among the teams tracking Tri Atlas, there are 3 things you need to do right now to become part of the scientific community registering this interstellar object in real time. Please hit the like button on the video right now so this discovery reaches more observers around the planet. Subscribe and turn on all notifications so you don't miss a single update on what's happening with Tri Atlas. And go down to the comments section this very second and write Tri Atlas to appear on the global registry of people actively following this historic event. Now, let us put into context why Tri Atlas has attracted so much attention and why a single date caused several observation centers to review their measurements with such care. Tri Atlas is an interstellar object, a traveler that did not originate around the Sun and that carries with it a composition and a history completely different from the bodies that belong to the solar system. Every time an object of this type approaches close enough to be studied with precision, astronomers obtain unique information about materials that formed in very distant places under conditions that do not exist here. That is why any change in its brightness, in its activity, or in its response to solar radiation becomes fundamental to understanding its nature. The 19th of December was not a date chosen by speculation, it was the object itself that marked it by showing a clear variation in the observation data. When a behavior does not match what is expected, astronomers have the responsibility to review what the instruments are showing, compare values, and verify whether the activity is temporary or indicates an important characteristic. That process, entirely based on real measurements, was what led the experts to pay more attention to that day. From this point onward, we will go through in a scientific yet accessible way why that variation was so relevant, how it was measured, and what role it plays within the current understanding of interstellar objects. The 19th of December began to stand out in the scientific records when several observation stations detected a variation that did not match the previously measured behavior of Tri Atlas. To understand why that day became so important, it is first necessary to clearly describe what type of object was being observed and why every change in its characteristics immediately arouses interest among experts. An interstellar object does not belong to the solar system. It was not formed with the same materials, did not follow the same evolution, and does not share the same dynamic environment that dominates our planetary region. That is why every time a fragment of matter coming from another system passes close to us, it represents an extraordinary opportunity to analyze physical and chemical conditions that do not exist in the Sun's neighborhood. Tri Atlas was catalogued following the same process applied to the other known interstellar visitors, based on the shape of its trajectory and its relative speed. A hyperbolic orbit is one of the clearest indicators of an external origin, and in this case the measurements confirmed that the object was not gravitationally bound to the Sun, but was simply passing through our spatial region before continuing its journey in another direction. Up to that point, the observation followed a relatively familiar pattern: brightness analysis, position tracking, monitoring of variations in the coma, systematic documentation of its behavior. As it approached regions more influenced by solar radiation, nothing outside the expected had yet occurred. However, as the measurements progressed, the photometric values that describe the intensity of the light emitted and reflected by the object began to show a stable rhythm that allowed a relatively consistent behavior to be projected. Those projections are fundamental because, based on them, specialists can know whether the object is gradually increasing its activity, maintaining constant emission, or presenting sudden changes that require re-evaluating the models. When those projections were compared with the data from subsequent days, the 19th of December emerged exactly as a point where stability ceased to be so uniform. It was not an extreme increase nor a change that suggested risk. What was relevant was its precision, the punctual way in which it occurred, and the fact that several instruments independently reported the same thing. To ensure that the change was real, the data were carefully reviewed. The observatories that performed the measurements corrected factors such as atmospheric interference, variations in detector sensitivity, thermal fluctuations, tracking conditions, and all the parameters that can accidentally modify a reading. Once the consistency in the corrected values was confirmed, it became clear that what was recorded truly corresponded to the object's behavior and not to an instrumental error. That verification reduced the possibilities of interpreting the change as a random fluctuation or noise in the signal. The observed variation was small but significant, and precisely for that reason it attracted so much attention. In astronomy, many times the important events do not manifest themselves in large bursts of brightness or dramatic visual transformations, but in discrete changes that reveal alterations in internal activity, in interaction with the solar wind, or in surface composition. In the case of Tri Atlas, what was detected was a modification in the light curve that did not follow the projected pattern, indicating that the object's material was responding differently to the solar environment or that some internal process was causing a momentary adjustment. The scientific importance of this behavior lies in the fact that interstellar objects are subjected to very different conditions before entering the solar system. They may have remained for millions of years in cold regions with almost no interaction with intense radiation, and their structure can be extremely sensitive when they approach the sun. Even a small amount of additional energy can generate an observable response. When an object like this presents a sudden variation, astronomers interpret that event as a window to study how its material behaves under a punctual change in temperature, radiation pressure, or interaction with charged particles. Upon reviewing the complete observation history prior to the date, scientists compared the magnitude of the change with the days before and after. The variation was neither recurrent nor persistent. It was a specific point within an interval that until then had behaved relatively uniformly. That indicates that the measured event did not correspond to a general trend, but to a punctual reaction that deserves attention because of the amount of information it can provide. Another relevant aspect is that the telescopes that recorded the variation used different methods to measure brightness and activity of an object. Some rely on broadband photometry, others on spectrometry, and others on automatic tracking techniques. When different instruments detect a similar pattern, the level of reliability increases notably. In the case of Tri Atlas, several observation centers independently confirmed that the change was neither isolated nor exclusive to a single system. That coincidence forced a more detailed examination of the object's structure in later phases to correctly interpret what could have caused that punctual response. As the reviews progressed, a key question arose. What specific conditions around the 19th of December could have influenced the behavior of an interstellar object that was entering a region where solar radiation was more intense? To answer that, experts analyzed variations in distance to the Sun, the inclination of its trajectory, the relative speed at that moment, and the solar wind conditions recorded during that period. Although none of those variables indicated an extreme situation, the set of data showed that the object was at a point where even a slight difference in energy could temporarily modify its activity. The interest was not based on alarm or speculation, but on the great scientific value of capturing such a punctual reaction. Interstellar objects provide information that cannot be obtained in any other way because they do not share the chemical history of bodies formed near the Sun. Each of their responses to radiation, heat, and solar wind helps build more accurate models about how matter that travels between stars evolves. That is why the 19th of December became a natural marker within the study of Tri Atlas, a point where science found a clue worth exploring in detail. To understand why experts gave so much importance to the behavior recorded around the 19th of December, it is essential to analyze the scientific principles that govern the study of interstellar objects and the reasons why their characteristics require a different approach from the one applied to bodies that do belong to the solar system. An interstellar object does not share the origin, composition, or dynamic history of the comets and asteroids that formed around the Sun. These are fragments of matter that were ejected from their systems of origin by intense gravitational interactions or by violent processes such as collisions between young planets or disturbances caused by nearby stars. That ejection does not occur randomly, but as a consequence of events that impose forces sufficient to break the orbital equilibrium that previously kept the object bound to its star. When a fragment of that type becomes free in interstellar space, it begins a journey that can last millions or even billions of years. During that journey it passes through extremely cold regions where radiation is minimal and outgassing practically does not occur. Unlike solar system comets that develop activity as they approach the sun and refreeze when they move away, an interstellar object may have remained stable for such a prolonged time that its internal materials are in a very different state from bodies that have undergone repeated thermal cycles. That is why every time one of these visitors approaches our environment, it offers the opportunity to observe how its structure responds to energetic conditions that it perhaps had not experienced in millions of years. The analysis of an interstellar object begins with the precise determination of its trajectory. The shape of the orbit is one of the most reliable indicators to distinguish it from an object originated within the solar system. Hyperbolic orbits, by definition, indicate that the object's speed exceeds the sun's escape velocity, meaning it is not gravitationally bound and that after passing through our environment it will continue its path outward without returning. In the case of Tri Atlas, the initial measurements quickly confirmed that its trajectory did not correspond to any known dynamic family and that its speed exceeded the typical values of bodies bound to the sun. That was the first step in identifying it as an interstellar visitor. Once its nature was confirmed, the next step consists of analyzing its apparent brightness at different time intervals to infer its activity. Photometry is one of the most important tools in this type of study because it allows the identification of variations in the amount of light the object emits or reflects. In solar system comets, those variations are usually associated with the sublimation of ices when they approach the sun. However, in an interstellar object, the quantity and type of volatile materials may be different, meaning its behavior may not follow the usual patterns. The response of its compounds to radiation may be more sensitive or more irregular due to its thermal history. In addition to photometry, spectra obtained by specialized telescopes provide crucial information about the object's composition. Spectra make it possible to identify which elements or molecules are present in the coma and on the surface and also to evaluate the temperature of the expelled material. In the case of Tri Atlas, the initial spectra collected by different observatories showed an unexpectedly intense and distributed signature, which reinforced interest in monitoring its behavior on short time scales. The importance of the scientific foundations lies in the fact that any variation, even small, can signal an ongoing physical process within the object. For example, if a material that had been in an extremely cold state for millions of years is suddenly exposed to a greater dose of solar radiation, it may suffer internal stresses that release microscopic fragments or temporarily alter its reflectivity. Although this type of event does not represent a risk, it is valuable because it reveals details about the cohesion and composition of the surface. Even a small adjustment in the brightness pattern can offer clues about the size and distribution of released particles or about how the internal structure is responding to heat. Interstellar objects also present additional challenges for their study because there is no prior history of their behavior. With solar system comets, astronomers can compare data from past approaches to the sun and analyze how they evolve over time. In contrast, an interstellar object is observed for the first time, meaning models must be built from scratch based solely on what the instruments record during its brief passage. That is why every datum is fundamental and every measurement has exceptionally high value. The 19th of December became relevant within this scientific context because it represented a point where the behavior of Tri Atlas deviated from the most stable pattern it had previously shown. To understand the magnitude of that change, experts reviewed not only the direct data but also the principles that explain why an object can react in that way under specific conditions. The physics of ultra-cold materials, the interaction between energetic particles and irregular surfaces, and the variability of solar radiation during that period form part of the theoretical framework used to interpret the observation. Comparison between different models showed that the observed variation was consistent with a physical phenomenon typical of objects highly sensitive to changes in temperature and radiation pressure. That coherence was what reinforced the importance of continuing to monitor the object, especially because each new datum could help validate theories about how materials originating from regions outside our solar system behave. As the analyses progressed, it became clear that the behavior of Tri Atlas fit within the expected scientific logic for an object with its origin and thermal history. The date was not an isolated factor, but the point where several physical principles coincided to generate a detectable response. That is what turned the 19th of December into an obligatory reference for the researchers who were documenting every detail of the object's behavior. The physical behavior observed in Tri Atlas during its passage through the inner solar system offered a unique opportunity to analyze how an interstellar object responds to energetic conditions that it may not have experienced in millions of years. Most bodies traveling from deep interstellar space regions preserve extremely cold, little processed, and highly sensitive materials to any increase in solar radiation. When an object with those characteristics enters an environment where sunlight is much more intense and the solar wind interacts directly with its surface, even small modifications can become visible through photometric and spectroscopic instruments. That is why every measurement made near the 19th of December had exceptional value, as it allowed specific traits of the object's behavior to be detected that had not been perceptible before. The brightness of Tri Atlas followed a relatively stable pattern in the preceding days, with small oscillations that fell within the expected range, considering the typical activity of an icy object progressively exposed to greater radiation. However, as it approached the region where solar energy began to influence its surface more directly, variations were recorded that indicated adjustments in its coma, a sign that the surface material was experiencing thermal stresses that could alter its reflectivity. These stresses are common in objects with fragile structures or compounds of ices that react quickly to increases in ambient temperature. The light curve is one of the most useful tools for studying this kind of behavior. When an object develops activity through sublimation, its brightness can increase due to the release of fine particles that reflect sunlight. In the case of Tri Atlas, the brightness intensity did not show an abrupt jump, but it did reveal a particular deviation in the expected rhythm. That deviation suggested that the object's surface was responding to radiation with a change that could be related to the temporary loss of material or a momentary redistribution of particles around its nucleus. What mattered was not the magnitude but the coherence of the change. Several telescopes that observed the object during the same period recorded the same pattern, confirming that the variation was real. The detailed analysis of images taken around that date showed slight alterations in the coma structure. Although these were neither dramatic nor implied extreme activity, the experts focused on identifying whether the coma showed an increase in its extension, a change in its density, or a shift in the direction of the expelled material. Preliminary studies indicated that the material around the nucleus seemed to respond to a momentary increase in energy, which corresponds to a physical phenomenon already observed in other icy bodies, albeit with different compositions. The interaction of the solar wind also plays an important role in this type of analysis. The solar wind is composed of charged particles that travel from the sun at great speed and can generate measurable effects when they collide with irregular surfaces or volatile materials. In interstellar objects, these impacts can be even more significant due to the fragility of their compounds. Upon comparing the solar wind speed values recorded around the 19th of December, experts identified that this period coincided with a moderate increase in the intensity of solar particles reaching the region where the object was located. Although that increase was not extreme, it did provide a possible physical explanation for the punctual response in the object's activity and the way the coma behaved. Under the influence of the solar wind, the way the coma behaves can reveal details about the internal cohesion of the material. For example, if the object expels particles that had previously remained attached to its surface due to thermal stresses, those particles can disperse differently depending on the solar wind speed at that moment. The analyses of Tri Atlas suggested that the material detached around that date had a slightly different distribution from that recorded in previous days, which reinforced the idea that the object had experienced a punctual change in its thermal equilibrium. Another important aspect of studying physical behavior is the object's rotation. Rotation can directly influence the way the surface receives solar radiation. If a specific region rotates toward the sun and contains materials more sensitive to heat, that area can release particles or temporarily modify its reflectivity, although the available data on the rotation of Tri Atlas do not yet allow its exact period to be determined with absolute precision. They did show variations in the light curve that suggest irregular rotation, a common feature in objects with low compactness structures. That irregular rotation could have contributed to the behavior recorded on the 19th of December. When these factors are combined, solar radiation, solar wind, fragile internal structure, and irregular rotation, a coherent picture emerges of how the observed punctual variation could have been generated. None of these elements implies an extraordinary phenomenon or one outside known physics. All fit processes already studied in icy objects, but in this case they become even more interesting due to the interstellar origin of Tri Atlas. Every reaction of an object like this is an opportunity to test theories and improve models that explain how matter traveling between stars behaves. The final analysis of the physical behavior around the 19th of December did not seek dramatic signals or alarming conclusions. What astronomers wanted to understand was how a fragment of matter so ancient and so little processed responded to a punctual change in its energetic environment. Science is based on patterns, and when a pattern deviates, even slightly, it offers information that can be key to better understanding the nature of that object. In the case of Tri Atlas, the deviation coincided exactly with that day, making it an indispensable reference point for any subsequent study. The orbital dynamics of Tri Atlas is one of the fundamental pieces to understand why every observed variation acquires scientific importance and why specialists paid so much attention to the behavior recorded around the 19th of December. The trajectory of an interstellar object does not follow the same patterns as bodies belonging to the solar system, which are gravitationally bound to the Sun and travel closed orbits that can be predicted with great precision. An interstellar object, on the other hand, moves along a hyperbolic orbit driven by a speed that exceeds the Sun's gravitational capacity to retain it. That characteristic completely defines the type of analysis that must be carried out to describe its motion, because every change recorded in its path, however small, can contain valuable information about its structure, its mass, its relative speed, and its interaction with the environment it passes through. The initial calculations of the orbit of Tri Atlas were performed as soon as the first confirmed observation points were obtained. To determine its exact trajectory, astronomers measured its position in the sky at different times and compared those data with orbital models capable of fitting hyperbolic curves. As more observations were gathered, the orbital parameters became more precise, revealing that the object had entered the solar system from a direction that did not coincide with the orbital planes of the planets, which is typical in fragments of interstellar origin. That pronounced inclination allowed confirmation that it was not influenced by local bodies and that its passage would be temporary, offering only a limited opportunity to study it. Orbit tracking also revealed that the speed of Tri Atlas was greater than that of almost any comet belonging to the solar system. That speed is direct evidence of its external origin, since a body that had formed near the Sun could not sustain an escape trajectory without having received extreme additional energy, something that does not match the typical processes that occur within the solar system. The high speed of the object made every observation critical, because small variations could go unnoticed if not analyzed with precision and frequency. That is why the instruments that monitored the object between December and the previous weeks maintained continuous records and cross-checks. As the object approached closer to the Sun, its trajectory experienced minimal deviations due to gravitational influence. Although the Sun could not capture it, it could slightly modify its path. The mathematical models used to describe that motion include parameters that represent both the object's speed and the gravitational influence exerted by the Sun and, to a lesser extent, by other planets. Each of these elements was taken into account to predict exactly where Tri Atlas would be at every moment, which made it possible to identify when it would cross regions where solar radiation would have a greater influence on its activity. It was in that phase of the analysis when the 19th of December began to acquire a significant role, because the calculations indicated that the object would be at a point where radiation would reach a level that could provoke a measurable reaction on its surface. The observations confirmed that Tri Atlas did indeed show a variation in its brightness around that date, and comparison with the orbital models allowed ruling out that the change had been caused by an error in the projection of its position. The object was exactly where it was supposed to be, which meant that any recorded variation was due to a real interaction with its environment. The coherence between orbital data and photometric data strengthened the scientific interpretation that the object's behavior responded directly to physical conditions and not to a deviation in the predictions. The orbital analysis also includes the evaluation of non-gravitational forces, an essential aspect in objects that release material. When an object expels particles or gases, that release can generate an extremely small thrust, but sufficient to slightly alter its motion. In solar system comets, this phenomenon is well documented and can modify the orbit in a detectable way over time. For Tri Atlas, scientists looked for signs of that type of non-gravitational thrust. Although the initial observations did not show a significant deviation, the variation recorded in its behavior around the 19th of December opened the possibility that small emissions of material could have contributed to tiny adjustments in its trajectory. The experts examined the subsequent data in detail to identify whether there was any indication of a slight deviation not attributable solely to gravity. Although the magnitude of any possible thrust was extremely small, the fact that it coincided with a variation in its surface activity reinforced the hypothesis that the object had a physical response to the increase in solar radiation at that point in the orbit. This type of analysis requires very high mathematical precision because the changes are so subtle that any error in the data could generate incorrect conclusions. That is why the measurements were verified again and again by different observation stations. Detailed knowledge of the orbital dynamics of Tri Atlas not only confirms its interstellar origin, but also helps interpret its activity changes appropriately. To fully understand an object that will not pass near the Sun again, it is essential to link every physical observation with the exact point of its trajectory. When orbital models are combined with photometric data, the relationships between the object's position, the intensity of the radiation it receives, the amount of solar wind that reaches it, and the changes that causes on its surface become clear. That combination explains why the 19th of December became an obligatory reference. It was the moment when the orbital models indicated a significant energy increase and when the instruments confirmed a direct response in the object's physical behavior. Orbital dynamics is therefore an essential tool for deciphering the history and structure of Tri Atlas. Every calculation helps place in context what the instruments are recording and allows the construction of a complete portrait of how a fragment of matter coming from another stellar system reacts while passing through our environment. Thus, the combination of orbital physics and direct observation forms the most solid foundation for understanding the scientific importance of this object and the relevance of the alterations detected on specific dates. The effect of solar radiation on Tri Atlas is one of the most important factors to explain why experts observed with such attention the activity recorded around the 19th of December. Solar radiation acts constantly on any object approaching the Sun, but its impact varies according to distance, the body's composition, and the time that material has remained in extremely cold conditions. In the case of an interstellar object, the thermal contrast is even greater because its compounds may have been practically inactive for millions of years in regions where the light of any star is barely perceptible. When that material suddenly enters a much more energetic environment, every molecule, every dust particle, and every ice fragment experiences stresses that can generate visible responses even from great distances. To understand the importance of this process, it is necessary to analyze how radiation acts physically. Sunlight carries energy that can heat the object's surface unevenly. If the surface contains volatile ices, these can sublimate, passing from solid to gaseous state without becoming liquid. This sublimation generates a flow of particles that disperse around the nucleus, forming a coma that can expand or contract depending on the intensity of the radiation, the amount of available material, and the internal structure of the object. In solar system objects, this behavior is common, but in an interstellar visitor the reactions can be more sensitive because its composition may include chemical mixtures that had never before been exposed to an energy increase of that magnitude. The records of Tri Atlas showed that as it approached the Sun, it began to experience a response that matched theoretical models of mild sublimation. It was not intense activity, but a progressive change in coma density compatible with the action of solar heat on a body with volatile materials. However, what caught the specialists' attention was the specific way in which that behavior manifested around the 19th of December. The variation recorded in the light curve showed a pattern that suggested a punctual alteration in the sublimation rate or in the reflectivity of the expelled particles. The coincidence between photometric analyses and trajectory calculations revealed that that date marked a point where the radiation received by the object reached a slightly higher level than in previous days, enough to provoke a reaction detected by the instruments. Solar radiation does not act uniformly on the entire nucleus. Depending on the object's rotation, certain areas may receive more heat than others. If a particularly heat-sensitive region rotates toward the Sun at a specific moment, that area can release particles that had remained attached for millions of years. This type of localized release can produce a temporary variation in the object's brightness, and that variation can be captured as a slight increase or drop in photometric records. The data from Tri Atlas matched this behavior, indicating that the object's surface may have presented thermal stresses that momentarily modified the quantity or distribution of particles around the nucleus. In addition to direct heating, solar radiation produces another effect known as radiation pressure. This phenomenon consists of the constant push that light exerts on particles, forcing their movement in the direction opposite to the Sun. In the case of an object with mild activity, radiation pressure can reorganize the expelled material, altering the shape and apparent density of the coma. When astronomers analyzed the images obtained around the 19th of December, they noticed that the dust distribution showed small differences compared to previous days. Those differences matched a scenario where even a slight energy increase could have temporarily modified the amount of material available to be pushed outward. The solar wind, which accompanies radiation, also plays an important role in this process. Composed of charged particles that travel at extremely high speeds, the solar wind can interact directly with the coma and generate variations in its orientation or structure. Activity measurements of the Sun carried out during that period showed that the solar wind recorded moderate fluctuations in intensity, which could have influenced the way the coma of Tri Atlas temporarily extended. The coincidence between these values and the variation in the object's brightness reinforced the scientific interpretation that the detected activity was a physical response to environmental conditions and not anomalous or difficult to explain behavior. Another important element in this analysis is the thermal conductivity of the nucleus. Interstellar objects usually have highly porous nucleus structures, meaning heat can penetrate unevenly into the interior. If a surface layer absorbs enough energy to sublimate a small amount of material, that release can change the internal temperature in adjacent zones, generating an expansion effect that can lead to the formation of microfractures. These microfractures can release particles that remain trapped, temporarily altering the coma density. That type of reaction is consistent with the data obtained around the 19th of December, suggesting that the object experienced a thermal adjustment that may have caused the release of small amounts of fresh material. Each of these processes, punctual sublimation, radiation pressure, solar wind, and internal thermal stresses, contributes to forming a coherent picture that explains why the behavior of Tri Atlas in that date attracted so much attention without implying extraordinary phenomena. The experts interpreted the variation as a physical phenomenon within the expected logic for an interstellar object exposed to an increase in radiation. The scientific value lies precisely in that coherence, the ability to record how a body with millions of years of history responds in real time to changing energetic conditions. The importance of the 19th of December did not lie in the magnitude of the change, but in the fact that it represented a point where theoretical models coincided with observations. Every response of the material, every modification in brightness, and every subtle change in the coma reflect physical processes that help understand how interstellar matter behaves under the direct influence of the Sun. That knowledge is essential to improve models of planetary formation, to study the evolution of primitive materials, and to understand with greater precision how fragments coming from other stellar systems travel and react when they temporarily enter our environment. The images captured by ground-based and space telescopes during the period when Tri Atlas showed the variation recorded around the 19th of December became a key piece to understand with precision what type of changes were occurring in its structure and activity. Direct visual observation, although it does not always offer the same numerical accuracy as photometric or spectroscopic data, allows the identification of features that can only be appreciated through high-resolution images, such as the texture of the coma, the presence of asymmetries, the dominant direction of the expelled material, or the existence of temporary fluctuations in its surface brightness. In the case of Tri Atlas, the telescopes that recorded images during that period showed details that perfectly complemented the information obtained by other methods, reinforcing the scientific analysis that the experts were developing. The first instruments that detected perceptible changes were large-aperture optical telescopes operating under dark sky conditions with tracking systems designed to capture fast-moving objects. The images obtained in the days prior to the 19th of December variation showed a faint, slightly diffuse coma compatible with a low level of sublimation. The nucleus was not distinguishable separately, as occurs in most comets observed at relatively large distances, but the distribution of material around the center of the object allowed inference that its activity was moderate and that the coma configuration was within the expected range for an interstellar body in the early phase of interaction with solar radiation. However, the images obtained during and after the key date showed slight differences in the shape and density of the material surrounding the nucleus. Although these variations were neither dramatic nor indicated extreme activity, they did reveal a physical response coherent with a punctual increase in radiation. Astronomers noted that the coma seemed to extend slightly toward a specific direction, which coincided with the recorded solar wind values. That extension suggested that a small amount of fresh material may have been released from the nucleus, generating a cloud of particles that was pushed by interaction with the solar environment. The behavior observed in the images also made it possible to identify whether there were linear or filamentary structures within the coma, features that can indicate material expelled at different speeds or with irregular distributions. In the case of Tri Atlas, some telescopes recorded zones where brightness seemed to concentrate momentarily, although these concentrations disappeared in later observations. That variation in surface luminosity is consistent with the temporary release of particles that reflect sunlight more effectively before dispersing or before radiation pressure modifies their direction. In addition to optical images, captures made at specific wavelengths allowed deeper examination of the object's behavior. Some telescopes equipped with specialized filters detected subtle differences in the distribution of dust-rich material and in the presence of certain volatile compounds. These observations did not imply the detection of new molecules or unusual phenomena. Rather, they showed a variation in the relative amount of particles released during that period. That information was essential to confirm that the activity of Tri Atlas was consistent with a controlled sublimation process that responded directly to the increase in solar radiation. Another relevant point was the analysis of images taken by space telescopes whose observations are not subject to atmospheric interference. Although these instruments cannot always point at objects with fast trajectories or positions close to the Sun, some managed to capture data that reinforced the analysis. Space images showed a better defined coma, free of distortions caused by atmospheric turbulence. This allowed the structure of the material to be compared with greater clarity and verified that the variations observed from Earth were not a consequence of the local environment, but inherent characteristics of the object. The detailed study of these images also made it possible to evaluate whether there were pronounced asymmetries in the coma distribution, which would have indicated localized activity or emission of particles from specific regions of the nucleus. Although no prominent jets or structures suggesting intense activity were detected, a slight elongation in a particular direction was observed, which is totally coherent with a punctual change in the sublimation rate or in dust redistribution due to radiation pressure. The temporal coincidence between this elongation and the analyzed date reinforced the interpretation that the 19th of December marked a point at which the object experienced a thermal adjustment. Image analysis is not limited to direct visual observation. Astronomers use advanced techniques such as differential photometry on images, which allows precise measurement of brightness intensity in each pixel. This technique revealed that the detected changes were not uniform throughout the coma, but were concentrated in specific areas, indicating that the physical process that produced the variation was localized and not generalized. Furthermore, the temporal evolution of those areas showed that activity decreased again in the following days, which is usual when the cause of the event is a punctual energy increase. The images also helped verify whether larger particles were being expelled, which could alter the observable dynamics of the object. Although the records showed no evidence of significant fragmentation or emission of large fragments, they did suggest the presence of smaller-sized particles that reflected light more intensely at certain moments. That type of behavior fits what has already been observed in other icy objects, where the sudden release of small dust grains can cause a local increase in brightness that diminishes as the particles disperse. The ability to correlate images with photometric and spectroscopic data was essential to build a consistent interpretation of what occurred. Each type of observation contributed a different piece of the puzzle, and together they formed a solid picture that explains the recorded variation without the need to resort to extraordinary hypotheses. The observed change was small, punctual, and completely explainable through known physical processes that affect cold objects exposed to solar radiation. That coherence between different observation methods is one of the most important elements within scientific analysis, as it allows conclusions to be validated with a high degree of certainty. Taken together, the images captured during that period not only confirmed that Tri Atlas was responding to solar environment conditions, but also provided visual indicators of how that response manifested itself. Science depends on corroboration, and the images offered exactly that, a visual verification of the physical behavior detected by other instruments. Therefore, the 19th of December was consolidated as a key point, not because it presented extreme activity, but because it allowed a clear reaction of the object to be recorded at different observation levels. The variations in brightness and activity of Tri Atlas recorded around the 19th of December became one of the central points of the analysis because they revealed subtle modifications that, although small, provided valuable information about the object's structure and composition. The brightness of an interstellar body does not depend solely on the light its surface reflects, but also on the amount of particles around the nucleus, their density, their size, and the way they are distributed. When changes are detected in the light curve, it is necessary to determine whether these are due to a real modification in the object's behavior or to a variation produced by the observation environment. In the case of Tree-I Atlas, the coherence between data recorded by different instruments confirmed that the variation was real and due to a physical response of the object to an increase in the energy it was receiving from the sun. The study of the brightness of an interstellar object is one of the main tools to interpret its behavior because it offers a direct view of how surface activity changes over time. In the days prior to the 19th of December, the light curve of Tree-I Atlas remained relatively stable with minor oscillations that fell within the expected margin for a body experiencing mild sublimation. However, on the indicated date a punctual change was detected that immediately attracted attention. The brightness intensity showed a variation that did not follow the projected pattern, indicating that the object had reacted differently to the solar environment at that instant. The analysis of this variation required understanding the different processes that can influence the light curve. One of them is the amount of material that detaches from the nucleus and disperses in the form of fine dust. These particles have the ability to reflect sunlight more effectively than the dark surface of the nucleus, so even a small release of dust can generate a temporary increase in observed brightness. For this reason, experts reviewed the images captured around that date to identify whether there was any signal indicating an additional release of particles. Some telescopes detected a slight expansion in certain coma zones, which coincided with a punctual sublimation phenomenon caused by the increase in radiation. Another factor that can influence the light curve is the redistribution of material around the object. The sun's radiation pressure has the capacity to reorganize the particles surrounding the nucleus, pushing them in a determined direction. If the solar wind reaches a moderate level in a specific period, it can temporarily displace the dust, changing the apparent density of the coma. This can cause variations in brightness without there necessarily being an increase in the amount of expelled material. In the case of Tree-I Atlas, the solar wind data obtained during that period indicated that its intensity had increased slightly, providing an additional explanation for the observed variation. Furthermore, the object's rotation can significantly influence its light curve. If the nucleus has zones with different degrees of reflectivity or different levels of activity, rotation can cause those regions to enter and exit Earth's field of view, producing smooth changes in brightness intensity. Although the available data on the rotation of Tree-I Atlas do not yet allow its exact period to be determined with precision, the variations detected in the preceding and following days suggest that the object might have irregular motion, which is common in bodies with little compact internal structures. That irregularity could have influenced the variation recorded on the 19th of December, especially if a region with greater thermal sensitivity was oriented toward the sun at that moment. Spectroscopic analysis also played an important role in interpreting changes in brightness. The spectra obtained around that date showed slight differences in the distribution of material surrounding the object. Although no new molecules or signals indicating extreme activity were detected, variations were observed in the intensity of certain bands associated with fine dust. That variation is consistent with the temporary presence of freshly released particles that reflect light more efficiently before dispersing or before radiation pressure modifies their trajectory. The coincidence between spectral variation and photometric variation reinforced the interpretation that the object had experienced a punctual adjustment in its surface activity. Another relevant aspect was the comparison of Tree-I Atlas data with records of other interstellar objects observed in the past. Although each interstellar visitor has unique characteristics, there are common patterns that allow certain behaviors to be anticipated. In previous studies of similar objects, punctual variations in brightness have been recorded when radiation reaches levels sufficient to cause thermal stresses. The variation observed in Tree-I Atlas coincides with these patterns, reinforcing the scientific interpretation that its interstellar origin contributes to its activity being particularly sensitive to changes in its energetic environment. The importance of this variation does not lie in its magnitude, but in its informative value. For astronomers, every change in the activity of an interstellar object represents an opportunity to study its internal composition, its surface structure, and the way it responds to external forces. The 19th of December provided exactly that type of opportunity, a point where the object's activity changed enough to be detected, but not so much as to lose stability or indicate an unusual phenomenon. That precision in behavior is what makes the obtained data especially valuable from a scientific perspective. When all observations are combined, variation in the light curve, adjustment in coma distribution, differences in the spectrum and solar wind data, a coherent picture emerges that is completely aligned with theoretical models of how an interstellar object responds to solar radiation. What occurred around the 19th of December was a perfectly explainable physical interaction, a small but extremely useful event to understand more deeply the nature of Tri Atlas and of other similar objects that may be detected in the future. Every detail recorded that day becomes one more piece in the construction of knowledge about the evolution of materials that travel between stellar systems and about the physical processes they experience when they temporarily enter the solar environment. The interest that space agencies showed in Tri Atlas during the period when the 19th of December variation was recorded did not arise from alarm or from an interpretation outside known scientific parameters, but from the importance that the international community attaches to every opportunity to study an interstellar object in transit through the solar system. This type of visitor represents one of the most valuable sources of information about matter that did not originate around the Sun, and each of its reactions to radiation, solar wind, and the dynamic forces of the environment constitutes a set of data that cannot be obtained in any other way. For that reason, agencies dedicated to astronomical observation, planetary research, and the analysis of minor bodies paid special attention to what occurred in that period, and they did so following the same principles applied to any object whose activity presents detectable changes. One of the elements that aroused the greatest interest was the precision with which the recorded variation coincided with the predictions of orbital models. The estimates established by dynamics teams indicated that Tri Atlas would be entering a region where solar radiation would increase enough to generate a measurable response. That prediction was fulfilled exactly, and this type of coincidence between modeling and observation is highly valuable for scientific research. Every time a theoretical model is confirmed with real data, its ability to describe future encounters with other interstellar objects is strengthened, and the interpretation of the physical processes that occur in those bodies is improved. For that reason, space agencies carefully reviewed the data corresponding to that date, understanding that they could validate predictions or provide new clues about the object's properties. Telescopes operating under international scientific collaboration programs also contributed to the analysis. Observatories managed by space agencies as well as ground-based research facilities compared measurements, light curves, and spectra to determine whether the detected variation represented isolated behavior or a signal that the object was entering a slightly higher activity phase. Although the data confirmed that the variation was punctual, they also showed that the object's response to the solar environment was within the expected range for an interstellar visitor. That coherence was considered a positive result because it allowed experts to build a more solid framework for studying similar bodies in the future. Another factor that generated interest was the opportunity to study how ultra-cold materials react when exposed for the first time to significant levels of solar radiation. It is known that solar system comets, especially those coming from distant regions like the Oort cloud, show intense responses when approaching the Sun. However, interstellar objects possess a different thermal history, and their behavior can provide information about formation processes that occurred far from the Sun. For agencies studying the evolution of primitive material, every variation recorded in the activity of Tri Atlas represented an additional datum about how icy surfaces respond to heat after having remained inactive for extraordinarily long times. Several space agencies and other specialized research centers in minor bodies paid special attention to the recorded photometric values, not because the variation represented a risk, but because it offered an opportunity to refine understanding of how interstellar visitors behave at different stages of their approach. The observed patterns matched phenomena of sublimation, surface thermal stresses, and temporary particle redistribution. That type of behavior is highly relevant to planetary science because the models that describe the formation of stellar systems are based largely on the interaction between icy materials and radiation sources. Furthermore, the fact that the variation coincided with a phase of increase in solar wind intensity generated additional interest among researchers. Agencies that constantly monitor solar wind conditions compared their data with the object's activity records, looking for correlations that could indicate how the interaction between charged particles and irregular surfaces influences the way the coma develops. Although the interaction was not extreme, it did show that even a moderate increase in solar activity can have a measurable effect on the distribution of material expelled by an interstellar object. This correlation is important because it helps interpret how the coma evolves and what factors can modify its appearance. The 19th of December also became a key point for other lines of research. Some agencies dedicated to comparative astrophysics used the data to evaluate differences between solar system comets and external objects, especially regarding thermal stability and internal cohesion. These analyses are fundamental to improving models that describe the formation of icy nuclei in different regions of the galaxy. The variations recorded by TRI Atlas offered a real example of how a body with a completely different history can react when exposed to an active stellar environment. On the other hand, teams specialized in orbital tracking carefully studied the possible non-gravitational forces that could have influenced the object's motion. Although variations in trajectory were extremely small, space agencies considered these data as an opportunity to evaluate how the release of small amounts of material can influence the dynamics of a body with relatively low mass. That type of study is valuable in the context of future missions that might approach objects of this type or even intercept them to take direct samples in subsequent decades. International cooperation also played an important role. Space agencies usually work together when objects that offer unique information to the scientific community are detected. The combination of data obtained from different hemispheres using telescopes with different capabilities allowed the behavior of TRI Atlas to be described with great precision. The agreement between records reinforced the validity of the scientific conclusions, offering a robust view of what occurred during that period. The importance of the 19th of December did not lie in dramatic expectations, but in the informative value of each of the recorded changes for space agencies. Every variation in the activity of an interstellar object represents an indispensable piece to reconstruct its history and better understand how it interacts with the Sun. That is the fundamental reason why attention focused on that date. It allowed the scientific community to observe, measure, and analyze an event consistent with known physical models and highly valuable for the advancement of astronomical knowledge. The scientific consequences derived from the behavior observed in TRI Atlas around the 19th of December are not limited solely to understanding what happened that day, but form part of a much broader framework that seeks to explain how interstellar objects interact with solar radiation and what information can be extracted from those interactions. Every variation recorded in activity, however small, adds a fundamental piece to the study of materials that have remained isolated from any intense energy source for millions of years. The analysis of this object therefore does not respond to an isolated curiosity, but to a global effort involving multiple scientific disciplines interested in understanding how matter that travels between stars behaves and what that means for the formation and evolution of planetary systems. One of the most relevant aspects that emerged from the study of the 19th of December event is the additional evidence that interstellar objects can react extremely sensitively even to small increases in radiation. Unlike solar system comets, which have experienced multiple approaches to the Sun and whose materials have already gone through repeated heating and cooling cycles, interstellar visitors preserve internal structures that can easily destabilize when exposed to solar energy. This extreme sensitivity provides a unique opportunity to study materials that probably originated in protoplanetary disks around other stars. When theoretical models predict that an object should show slight activity at a certain distance from the Sun and observational data confirm that prediction, the validity of those models is reinforced. This happened precisely with TRI Atlas. The recorded variation coincided with calculations indicating that the object would be entering a zone where solar radiation would reach levels sufficient to trigger surface thermal stresses. The fact that this behavior was fulfilled exactly as projected means that current models on sublimation of ultra-cold materials are on the right path and can be applied to future interstellar visitors. Another important aspect is the contribution that these data offer to the study of the distribution of volatile compounds in interstellar objects. The observations of TRI Atlas showed that its activity was moderate but perceptible, suggesting that the object contains materials that react even to small energy increases. This strengthens the hypothesis that objects traveling from other stellar systems can preserve a mixture of compounds that varies significantly depending on the place of origin and the stellar environment in which they formed. Every thermal response is essentially a clue about the composition hidden beneath the object's surface. The study of the coma provided additional information. The slight expansion of material recorded around that date showed that even under low-activity conditions, structural changes can be observed when instruments have adequate sensitivity. This observation is particularly relevant for comparing TRI Atlas with other interstellar objects studied in previous years. Although each one has its own characteristics, the tendency for them to show moderate but radiation-sensitive activity seems to be repeating. This reinforces the idea that interstellar materials tend to preserve a significant level of trapped volatiles in their nuclei, volatiles that can be released when thermal conditions change suddenly. Another central point is how these data help improve understanding of the structural stability of objects that have traveled between stars for extremely long periods. If an object is capable of maintaining its cohesion after millions of years of travel, it means its nucleus possesses an internal structure that could have withstood multiple external stresses. However, the variation recorded in TRI Atlas suggests that although its overall structure remains stable, its surface can react quickly to energy increases. This provides an interesting balance between global stability and surface sensitivity, a trait that may be common among interstellar bodies. The movement of the expelled material around the 19th of December also offered important clues for studying the interaction between radiation pressure and expelled dust grains. The models that explain how sunlight pushes these particles can be refined thanks to the data obtained in this case. This not only provides information about the behavior of TRI Atlas in particular, but also contributes to improving simulations used to predict the activity of future interstellar visitors. The more precise the description of dust movement, the easier it will be to interpret the nature of these objects. Furthermore, the data obtained on this date allowed progress in understanding the role played by the solar wind in modifying the coma of an interstellar object. The interaction between charged particles and icy nuclei from other stellar systems is a line of research that is just beginning to develop. The variations observed in TRI Atlas help characterize how these bodies can react under specific solar wind conditions and provide a basis for future studies. The variation also allowed reflection on the temporal evolution of interstellar objects during their passage through the solar system. Although the recorded activity was punctual and not persistent, its appearance offers evidence that these bodies can experience brief episodes of thermal response that disappear as quickly as they appear. This characteristic is essential to understand why some interstellar objects show irregular activity or why certain features are only detected in very precise intervals. Science depends on capturing these moments, and the 19th of December represented one of them. Finally, the scientific consequences of this observation go beyond the study of a single object. Every fragment of information obtained from TRI Atlas contributes to building a more solid framework to interpret how other stellar systems formed and how their primitive materials evolved. Interstellar visitors are messengers from the deep past, carriers of compounds that may have arisen under conditions very different from those existing in the solar environment. Therefore, every measured reaction, every detected variation, and every recorded behavior adds understanding about the processes that gave rise not only to our solar system, but also to distant stellar systems that we can never study directly. What still remains to be understood about TRI Atlas is as important as everything already known, because every interstellar object that crosses the solar system leaves more open questions than it answers. Although the data obtained around the 19th of December allowed identification of how it reacted to a punctual increase in radiation, a wide margin of research still remains to determine what internal characteristics allowed that variation to occur in the way it did. The greatest limitation in the study of an interstellar visitor lies in the fact that it can only be observed during a relatively short period, and when it continues its trajectory outward, it is no longer possible to follow its evolution with the same precision. That is why the analysis of every observation made during its approach to the Sun is crucial to try to reconstruct processes that can no longer be measured once the object leaves our environment. One of the aspects that still requires further research is the exact composition of the nucleus. Although the obtained spectra offer clues about some compounds present in the coma, identifying the precise mixture of elements and molecules inside the nucleus is extremely complicated from a distance. The variation recorded around the 19th of December suggests that the object contains volatile materials that react immediately to increases in solar radiation. However, it cannot be determined with certainty whether those materials are similar to those found in solar system comets or whether they come from chemical processes that developed under different conditions in a protoplanetary disk around another star. This question is fundamental because it could offer information about the chemical diversity of other stellar systems and about differences in planetary formation processes. Another aspect that requires additional study is the internal structure of the nucleus. The way an interstellar object fractures, releases particles, or responds to thermal stresses depends largely on its internal cohesion, material density, and level of porosity. In solar system objects, this type of information is obtained by comparing multiple approaches to the Sun, but in the case of an interstellar visitor only a single passage can be analyzed. The variation recorded on the 19th of December could be a sign that the nucleus experienced internal stresses that released small amounts of material before stabilizing again. However, without prolonged observations after its exit from the solar system, it is difficult to confirm whether that behavior is part of a broader pattern or whether it was an isolated event. It also remains to be understood with greater precision how expelled dust grains interact with radiation pressure and the solar wind in the case of interstellar objects. Although current models provide a solid framework for interpreting these interactions, each new interstellar visitor offers an opportunity to validate or adjust those models. The behavior of Tri Atlas around the 19th of December showed that the expelled grains seemed to reorganize temporarily due to radiation pressure, but it is still unknown exactly what size those particles had or what optical properties influenced their reflectivity. Understanding these details would help complete the picture of how interstellar particles behave under variable energetic conditions. Another open question is how the irregular rotation of the nucleus influences its overall behavior. The small variations in the light curve before and after the 19th of December suggest that the object might have a complex, perhaps non-uniform rotation period. If the object presents regions with different thermal sensitivity, rotation could expose those areas to the sun unevenly, generating localized sublimation events that manifest as punctual variations in brightness. However, the exact rotation period could not be determined with precision due to the limited amount of available observations. Having more data would allow identification of whether the observed variation was caused by a specific zone of the nucleus or by generalized behavior of the surface material. Questions also arise about the complete history of the object before entering the solar system. It is not known exactly from which stellar system it comes or how long it has traveled through interstellar space. Current models suggest that these bodies can spend millions of years in cold regions far from any significant energy source. During that time, its surface can slowly modify due to the action of high-energy cosmic particles, generating an outer layer that can behave differently from the deeper material of the nucleus. The 19th of December variation could have been a manifestation of that internal difference with the temporary release of material that had remained protected inside. However, confirming this hypothesis would require data that can no longer be obtained now that the object continues its path outward. Despite these limitations, the case of Tri Atlas offers an exceptional opportunity to improve theoretical models on the behavior of interstellar objects. Every observation, however minimal, contributes to completing a broader pattern that is being built from the few interstellar visitors detected so far. The fact that the observed variation coincided exactly with predictions about how an ultra-cold object should react upon reaching a specific region of solar radiation indicates that the theoretical base used is solid. At the same time, the minor differences with respect to other studied objects offer space to adjust the models and improve their predictive capacity. The 19th of December event also invites reflection on the importance of continuous sky surveillance. The early detection of Tri Atlas allowed multiple observatories and space agencies to coordinate their efforts to collect data that would otherwise have been lost. Science depends on opportunity, and in this case the coincidence between prediction and observation allowed the recording of a brief but highly informative episode about how interstellar matter reacts under solar conditions. What remains to be understood does not diminish the value of what has already been learned. On the contrary, it highlights that every interstellar object is a unique opportunity to deepen knowledge of formation processes, the chemistry of primitive materials, and the evolution of icy bodies that travel between stars. Tri Atlas, like its predecessors, has provided data that will enrich science for years, even though its passage through the solar system is brief and it will never return. Every recorded variation, every measured change, and every identified behavior form part of the scientific legacy it leaves behind as it continues its journey toward regions we can never observe directly.